All right, hello, welcome to our 11 a.m. news briefing on Voyager 2. Our speakers this morning are Nicky Fox, Director of the Heliophysics Division at NASA headquarters, Ed Stone, Voyager Project Scientist at Caltech, John Richardson, Voyager Plasma Science Experiment Principal Investigator at MIT, Georgia Denolfo, Cosmic Ray Scientist at NASA Goddard Space Flight Center. And here for the Q&A is Suzanne Dodd, Voyager Project Manager at NASA's Jet Propulsion Laboratory.
Good morning. Voyager has a very, very special place for us in heliophysics. If I can, okay. It would if I could advance my slides. There we go. So heliophysics really is the study of everything in the heliosphere. It is our place in space, if you like. Very recently, we launched the Parker Solar Probe mission, which of course was humanity's first trip right into the sun's corona, the kind of driver of everything that shapes our heliosphere. It's named for Gene Parker, everybody knows that. But Gene Parker's theory was more than just explaining the corona. It also explains why there is a heliosphere, why there is a boundary that protects us from interstellar space. It really shapes our place in the universe. The solar wind expands away from the sun, it bathes all of the planets, and of course it creates this bubble that extends far past the orbits of all of our planets, and it's kind of shaped like a long windsock, and it protects us as we move through interstellar space. The leading edge of the heliosphere is much closer, and so fortunately we sent Voyagers in that direction, otherwise we wouldn't be here today. Changes in the conditions in the solar wind really change the shape and the size of our planetary magnetospheres, but they also change the shape and the size of our heliosphere. So literally our heliosphere kind of breathes in and out on the timescales of a solar cycle. So we have been, imaging our place in space with the Ibex mission for over 10 years. It has been taking images of the heliopause of that final boundary. We're also looking forward to a new heliophysics mission that will launch in 2024 called IMAP that is going to do even more of the imaging. And I'm pleased that the principal investigator of both these missions, Dr. Dave McComas, is here should you have any questions later at the end of the briefing. Of course, as we say with when we launched Parker Solar Probe, we've taken so many images of the sun, but nothing is really like taking those steps, taking that journey into the region to really visit it for yourself. And so, of course, that is what we have done with Voyager. We have gone to the very outreach of the edge of our heliosphere. Back in 2012, we know that Voyager 1 crossed that boundary and is in interstellar space. As you know, because we had a press release, and of course Dr. Stone gave a very good paper this morning, you know Voyager 2 has also crossed out through the heliopause into interstellar space. What was very exciting for us was, of course, with Voyager 1 having done it in 2012, we knew the signs and we knew really what to look for. And so we've been really waiting with bated breath for the last couple of months for us to be able to see this. And Ed is going to do a very nice job of giving you kind of how we knew we were nearing the heliopause and what signs we were looking for because we'd already seen it from Voyager 1. This time is an even better time for us because there is an extra instrument that is still functioning on Voyager 2 that gave us a crucial measurement that was missing that really helped us be able to say with a lot of certainty we've crossed the heliopause. And Dr. John Richardson will be talking about that. Finally, Georgia Denolfo is going to kind of put into context why these measurements from outside our heliopause are so important to us here. Just because it's outside our neighborhood doesn't mean that it doesn't have a profound effect on what we see here. Now, I often get asked, so is this it for Voyager? You've crossed out of the heliopause, is it done? Are we finished? Absolutely not. This is really, for me, the beginning of a new era of heliophysics science. We have Parker Solar Probe up there telling us what is driving all of this activity that shapes our heliosphere. And now we are fortunate enough to have two very brave sentinels that have left our heliosphere and are out truly looking at the other side of the boundary in our interstellar medium. And so without further ado, I will turn it over to Ed, who is going to start with all the really interesting Voyager results.
Thank you, Nikki. This is a very exciting time again in Voyager's 41-year journey so far of exploring the planets and now the heliosphere and entering interstellar space. Let's see, I can do this. This is Nikki mentioned that we're inside this bubble that the sun creates around itself. When Voyager was launched, we didn't know how large the bubble was. We didn't know how long it would take to get there, and we didn't know if the spacecraft could last long enough to get there. But fortunately, Voyager 1 got there in 2012 at a little over 11 billion miles from Earth and entered interstellar space. And the question is, why did we say we did? Well, there were three key things which we relied on. Number one is there are lots of cosmic rays out in the Milky Way galaxy trying to get in. And some of them do get in, but many of them don't. And so we were looking to see that the intensity of cosmic rays increased as we approached the boundary and then jumped up to its final values. Same time, there are heliocentric particles which originate inside the bubble, and they want to get out. And so we expected to see that as we got to the edge, they would rapidly disappear into the vastness of interstellar space. And the third thing we expected to happen was that the magnetic field outside the bubble is from the Milky Way galaxy, and it would be, so we would see a jump in the intensity of the field at the boundary between the two winds. There are two winds pushing on each other, the solar wind from the inside pushing out, and the interstellar wind pushing back in balance. And that, as Nicky said, varies with time. Here's the spacecraft that's been doing all this. This long boom is where the magnetic field magnetometers are to measure the magnetic field because it's very weak and you want to be away from the spacecraft. The cosmic ray instrument is here. It measures particles coming from the Milky Way galaxy and also some from inside. There's a second lower energy charged particle experiment, as you can see also on this boom. And this is where the plasma science instrument is, which works on Voyager 2. Unfortunately, was not working on Voyager 1 at the time. And you see two antennas, which are the antennas used by the plasma wave to detect the density of what's out there whenever the sun cooperates and creates enough noise for the heliosphere to sing. This shows you the two different counting rates. The top one is the counting rate of the galactic cosmic rays, so you'll see it increase as we'll see it increase as we approach the heliopause. This is, of course, Voyager. This is now what Voyager 2 did. Now you can see the top one is the galactic cosmic rays. See them increasing, and then suddenly we're up there, and that's where we are now. If you look at the lower plot, you'll see that at the same time, exactly the same day, the inside particles took a big step downward and now have continued down. This is not exactly what happened on Voyager 1, and that's what makes it interesting because we're at a different place. One's in the northern hemisphere, the other's in the southern hemisphere, and it's a different time in the solar cycle. We would have been amazed if it looked the same, and that's what makes this interesting. We still have things to explore in the nearby interstellar space as the two spacecraft now continue their journey of exploration. And this is just a more technical plot of what that video was about. If you see the red, that's what we saw on Voyager 1. The blue is what we saw on Voyager 2. And you can see it's getting to the point where we will have the same intensity at both places. And this is the particles that are outside getting in. Here are the particles inside getting out. And notice the transition was different. Voyager 1 had series of small depressions before finally leaving. And Voyager 2 after the heliopause has the inside particles continue to fill the nearby interstellar space, and that's one of the things which we need to explore as well. We also have a magnetometer, and first time ever we have measuring the solar wind itself, the thing which in fact creates this bubble over the 11-year solar cycle. So I'll turn it over to John Richardson.
Good morning. I'm happy to be here because that means we finally have plasma data from near the Heliopause. As you've heard several times, Voyager 2 is the first spacecraft with plasma data instrument to get there. Voyager 1's instrument failed in 1980, so we've had to wait 6 years longer than all the other experimenters to see what's going on. So the plasma instrument measures the ionized gas moving in the solar system, mainly made out of protons and electrons. We measure the lowest energy particles. These are the particles that make up most of the population. This is a plot similar to the one Ed showed before, except now we have added streamlines showing the flow direction of the plasma. The solar wind is moving directly outward from the sun initially, and this forms the bubble in the interstellar medium called the heliosphere. At the termination shock, which Voyager 2 crossed in 2007, the flow turns and goes along the heliopause boundary. The other plasma we have is the interstellar medium, which moves in towards the nose of the heliosphere and then turns to deflect around the heliosphere. This is our instrument. It is designed specifically to measure the solar wind plasma. We have these 3 Faraday cups, which are pointed back towards the sun, and one looking sideways to see flows in other directions. So when we cross the heliopause, we expect the solar wind plasma to go away, and because we're across the boundary and in the interstellar plasma. And if you look at these 3 plots, these are currents measured in these 3 cups that are pointing towards the sun. And you see that at this point, the fluxes start to decrease, and at day 309, they drop out at the same time in all 3 cups. So we're not seeing the solar wind anymore. That means that we must be inside the interstellar medium. This shows the plasma parameters we measured just before we crossed the heliopause on the top. This is the density. You see it jumped up just before the heliopause crossing. The speed went down just before the heliopause crossing. This is roughly what you expect if the flow is running into the heliopause and being stopped and compressed. And just after we saw the heliopause crossing is when Ed Stone showed these galactic cosmic ray increases and a decrease in heliospheric particles, which is also what you expect to see at the heliopause. In the session this morning, we learned that at this point, the magnetic field also increased, and Rob Decker showed us that the lower energy energetic particles also dropped out at this point. So everything is consistent with us seeing the heliopause crossing on Voyager 2. So now what we have left is for Voyager 2 to explore the interstellar medium.
I'm not a member of the Voyager team, but I've been studying galactic cosmic rays for many years from within our heliosphere. So it's especially exciting to be able to think that we will be having a mission in the very same space that I have been studying and many others from afar. Voyager 1 and Voyager 2 will actually give us a first-hand view of the local galactic neighborhood outside of the heliosphere. So while we are moving out of that protective bubble that we call our heliosphere, we'll actually be entering into a much larger bubble. It's 100,000 times larger than our own heliosphere, and it is filled with a tenuous million-degree gas. The local bubble, as we call it, was actually produced by a sequence of supernova blasts that occurred within the last 10 to 20 million years. Within the last several 100,000 years, our solar system has been located in a filamentary cloud within our local bubble that is filled with relatively cool and dense interstellar material. We've been able to actually measure some of those neutral particles as they drift into our heliosphere, but But with Voyager 2, we'll actually be able to measure the local plasma and its embedded magnetic fields. We'll not be in the local cloud forever. We're actually drifting out. And as we do so, our environment will change, and so will its influence on our heliosphere, perhaps changing the shape of our heliosphere and the permeability to galactic cosmic radiation. So the major source of galactic cosmic radiation at Earth that we observe is in the form of galactic cosmic rays. These are fast-moving particles at nearly the speed of light, whose mass spans the periodic table. Our heliosphere acts as a force field so that only a fraction of those cosmic rays can reach us at Earth. Even so, galactic cosmic rays pose a serious threat to our space assets and also a health hazard for human exploration. So one of the things that I wanted to point out that's exciting, I think, is that galactic cosmic rays act as tiny messengers of our local galactic neighborhood. And oops, and I'm not doing the advancing, so let's do that. So this is our local bubble. And inside it, you can see these filamentary clouds that I've been talking about. And so what I would like to talk about is the fact that our galactic cosmic rays act as tiny messengers of the local galactic neighborhood. And so we know that, for instance, because the radioactive isotopes within galactic cosmic rays act as clocks, and they can actually help us to piece together a timeline for the major events throughout the cosmic ray lifetime. So what that timeline is actually telling us is that there's a very particular place in our galaxy where cosmic rays are both created and then accelerated to the extreme energies that we observe. And that is within clusters of massive stars called OB associations. And so what I'm showing here is the nearby Orion Nebula that is part of the Orion OB association, which is actually visible to the naked eye in the winter sky. And it just so it ends within these OB associations, supernova events occur frequently enough and are close enough together so as to be able to accelerate freshly synthesized interstellar material. And it just so happens that OB associations played a critical role in forming our own local bubble. So we live in an exciting time when the discovery of exoplanets has provided a very real possibility for life on other planets. We have remote observations that are telling us a lot about these planets and also about how the progenitor star influences the evolution of these planets, perhaps acting as a catalyst for life. Our own heliosphere serves as a local laboratory so that we can actually study the heliosphere of other stars, which we call astrospheres. And we've actually been able to detect many astrospheres in our local galactic neighborhood. So for me, this is an extremely exciting time for the history of space exploration, where we're able to actually look at the galaxy through the clouded lens of our heliosphere, and now take a step outside with Voyager, and for the first time, contemplate the vistas of our local galactic neighborhood.
Hold on one second. Okay, great. Thank you. We'll now take questions from any reporters in the room. This is just a reminder that only registered reporters may ask questions. Please state your name and affiliation.
Seth Borenstein, the Associated Press. I guess for John or any of you, is there anything you have seen with the plasma science experiment that you can tell us in terms of new findings that you did not see in Voyager 1? Or is there any other things that about this area of interstellar space that's different than the area that Voyager 1 was already in?
Well,
Press it.
is it on?
It's on.
It's on. Okay. Well, one thing we discovered was that there's a boundary layer about 1 AU in width before the heliopause. We'd seen before that the galactic cosmic rays went up in this region, but now we know that this is where the plasma speed actually started to decrease and the plasma density increased. I think we're also surprised by how quickly the plasma speed decreased just in front of the boundary. We thought it would be a more gradual decrease, but we went from 60 or 80 to 20 in only a few days.
Harvey Lyford, freelance. For Dr. Denolfo, I didn't quite get what you said about the mass spanning the entire periodic table. Was that of the rays or of what? And you really mean that every element is in it, or what?
Well, sure. Galactic cosmic rays come in they're all sorts of particles, and from hydrogen to helium to iron to ultra heavy. And so that's what I meant by spanning the periodic table.
Over here, Lauren.
Hi, this is Megan Bartels from space.com. A question for you, Ed. Could you talk a little bit about your having had the experience of Voyager 1 crossing this boundary and then having the years of waiting for Voyager 2 to follow suit and then having this slightly different experience? What was that like for you emotionally as a scientist?
Well, one of the great things about Voyager is it keeps surprising us, which really means there's a lot to learn. And so I would have been surprised if it had looked the same as Voyager 1, because that would be amazing. It turns out we've seen a different part of the boundary at a different time in the solar activity cycle, and so we're learning a lot about the differences as well as the commonalities.
Are there any other questions from reporters in the room?
Hi, Jeff Faust, Space News. This might be a question for Suzanne Dodd. What's the health of Voyager 1 and 2, and how much longer do you expect to get data from them?
Well, what I like to say is both spacecraft are very healthy if you consider them senior citizens. They are operating just fine. Our biggest concerns are both power and thermal. We lose 4 watts of power a year, so that means we have to continue to shut off systems on the spacecraft in order to keep the instruments operating. Also, Voyager 2 in particular is very cold. It's currently at about 3.6 degrees Celsius is the temperature it's flying at. And that's close to the freezing point of hydrogen, so that we're really worried about our plus roll thruster. So we have to make a lot of trades, particularly with Voyager 2, between power and thermal, and leaving something on in order to keep the spacecraft warm enough to continue to operate. But looking ahead, and I know a lot of science data ahead of us still, we anticipate we can operate for anywhere from probably 5 or 6 to almost 10 more years. And that won't be with all the instruments on, and the difficult decisions are going to be made by Dr. Stone and the science team on which instruments to turn off first. And each instrument also has a heater, so we would obviously turn off the heater first before we actually turned off the instrument. But we do have difficult decisions ahead, but those decisions will be made with getting the most science value back as we go forward. And I'd just like to add that my own personal goal would be to get these spacecraft to last 50 years. So we launched in 1977. If we get out to 2027, that'll be a 50-year mission, and I think that would be fantastic.
We agree.
Are there any questions on the chat?
Hello. There are 3 questions.
Ask one at a time, please, and state who it's from.
Okay, so the first question is from Jonathan O'Callaghan of Scientific American. His question is for Ed Stone. Why is November 5th the official leaving date? What measurements on that day confirmed you were beyond the heliopause? From the charts, the number of ions were much higher on this day for Voyager 2 than the comparative day that Voyager 1 is said to have crossed the heliopause. So just looking for some clarification.
Yes, well, you did see in the plots, and they went through by very quickly, but the November 5th was the day that the galactic cosmic ray intensity abruptly increased. That same date was the time when the heliospheric particle intensity dropped significantly that same day. The magnetic field increased on that same day, that's also when the plasma probe quit measuring the solar wind on that very day. So that's the correlation that we were looking at in terms of that day.
The second question is from Irene Klotz of Aviation Week and Space Technology. This is also for Dr. Stone. When are Voyager 1 and Voyager 2 RTGs expected to stop generating enough electricity for science collection and communication? Also, what's the present location of Voyager 1?
Well, Susie Dowd has already answered the question about the lifetime issue, heating and power for instruments and heaters.
Okay, and then the third question is from Kenneth Chang of the New York Times. What has Voyager 1 learned about interstellar space in the past 6 years?
Well, what we've learned, for instance, among other things, is what the intensity of the galactic cosmic rays are. We had no idea. They could have been much more intense than they are. We already now know that, in fact, typically only 70% of only 30% of what's outside can get into Earth. That's the shielding that the heliosphere provides, and that we determined because for the first time we measured what's outside trying to get in.
Seth Borenstein, Associated Press. And just for us, which of the two Voyagers, actually, if you could tell us which star is closest to the two Voyagers and how far is it before they get to the next? You said, I'm trying to remember who, I think it was Nicky who said that they're going to be leaving the interstellar bubble. Where are they next? And what's closest to both of them?
Well, it's about 40,000 years before they are closer to another star and in fact, they'll still be over 1 light year away from those stars. And in fact, the encounters with those stars is such that the star is moving at 100 kilometers per second, Voyager is moving 17. So in a certain sense, the star is encountering Voyager rather than Voyager is encountering the star. These stars move around a lot, even though, and of course they're in orbit around the Milky Way galaxy, typically with several hundred kilometers per second in their orbit. And that's what this two spacecraft will be in the same kind of 225-year orbit around the center of the Milky Way galaxy for basically billions of years.
So which one, I know it's silly, but which one is likely to be closer first to the in 40,000 years?
Well, I think the first order, it's about the same, okay?
Are there any other questions from reporters in the room? Are there any other questions on the chat?
Yes, there are two questions on the chat. Irene Klotz would again of Aviation Week and Space Technology would like to repeat her question of the location of Voyager 1. And the second question is from Lisa Grossman.
Let's answer that first question first. Where is the location of Voyager 1?
Where is Voyager 1 now? Voyager 1 now is about 140 some AU. The boundary of Voyager 1 crossed it was at 122 AU, so it's well beyond the boundary now, but it's still in the region that you can see where the interstellar wind is perturbed by the fact it's running into the heliosphere. It's plowing into the heliosphere.
Okay, and the next question is from Lisa Grossman of Science News. She says, is it certain that Pioneer 10 and Pioneer 11 have not crossed into interstellar space? How long will it take to get to the Oort cloud?
How long will it take to do what?
To get to the OORT
Oh,
cloud.
about 300 years, as I recall, to get to the inner edge of the Oort cloud, and 30,000 years to get on the other end of the other side of the Oort cloud.
Okay, and then we have another question from Jonathan O'Callaghan. What is believed to be the primary driver of the distance of the Heliopause? Is it solar activity or the galactic magnetic field?
So it's really a balance between the two. So that is where our boundary, it's where the solar wind kind of peters out. If there wasn't an interstellar wind, the solar wind would keep on going forever. But it balances out where it meets that interstellar wind. And that's why the whole boundary breeds as the solar cycle changes. And so when the solar wind is stronger, the heliosphere is bigger and more inflated, and when the solar wind is weaker, the heliosphere is much smaller. Well, not much smaller, but it is significantly smaller.
We have another question from Lisa Grossman. Would you say that the Voyagers have left the solar system? If not, why not? Is there a more precise way to say what they've done?
You want to answer that one? The solar system includes all the comets which form this cloud well beyond where Voyager will be when it runs out of power. As I said, it's 300 years just to get to the inner edge of the Oort cloud. So the comets are part of the solar system. So it's sort of halfway to the next star. The sun's gravity controls, and when you're closer to another star, its gravity controls what's being orbited.
That's all the questions.
Are there any other questions from reporters in the room? Are there any additional questions on the chat?
No more questions.
Okay, great. That concludes our press conference. Thank you very much.
Okay.
Questions from scientists in the room, huh?